Welcome to today's Explainer. Today we are diving headfirst into the engineering realities behind waste to energy. Look, we all know the global waste crisis is a massive problem, but moving from that feeling of crisis to an actual structured engineered solution, that requires a very strict methodology. So we're going to examine the exact technical frameworks and conversion pathways that allow us to process the materials society leaves behind.
Let's kick things off by anchoring ourselves to a number that's honestly pretty staggering: 2.01 billion. That is the amount, in tons, of municipal waste generated globally in the year 2016 alone, according to the Asian Development Bank. And projections suggest this could literally hit 3.4 billion tons by 2050. To put that into perspective, a leap of that magnitude doesn't just mean we need more collection trucks or bigger landfills, it fundamentally threatens our existing civil infrastructure and environmental stability. Energy supply and waste management are deeply connected challenges, and tackling them requires precise, scalable engineering.
Now, what's really interesting here is that waste isn't just one monolithic pile of trash. Almost half of it, 44%, is organic food and green waste, and over a third is dry recyclables. Treating all of this exactly the same is, well, an engineering impossibility. Understanding this specific composition is absolutely crucial. I mean, you simply can't process wet, dense food scraps using the same thermodynamics you'd use for dry cardboard or synthetic plastics, right?
So here's our blueprint for today. We'll be looking at 1. The Global Waste Challenge. 2. Enter the circular economy. 3. It starts with feedstock. 4. 3 pathways to power. 5. Opportunities and major risks. And finally, 6. The engineer's decision framework.
Let's jump right into Section 1, the Global Waste Challenge.
Here is the harsh reality. At least 33% of global waste is openly dumped or left completely unmanaged. In a lot of developing regions, the absolute lack of collection infrastructure makes open burning the default method of disposal, and this heavily skews the emissions baseline. When environmental engineers are evaluating if a waste-to-energy project is viable, they aren't comparing it to some pristine, state-of-the-art recycling utopia. No, they're calculating the net benefit against the reality of toxic open burning, unmanaged methane release, and localized groundwater contamination.
Moving on to Section 2, enter the circular economy.
We absolutely have to change our entire philosophy about how materials flow through our world. In the old linear model, materials are taken, made, used, and then just tossed out. But a true circular economy demands that we keep materials in play through recovery, reuse, recycling, and upcycling. In this new framework, waste to energy is not some magic bullet meant to consume everything. It's a calculated treatment used strictly for the difficult residuals, the leftovers basically, only after we've exhausted all our reduction and recycling protocols.
Now that we understand that philosophy, let's look at the raw materials in Section 3. It starts with feedstock.
You really have to know this term because the entire engineering reality pivots on it. Feedstock is the specific waste or biomass material you're supplying to a conversion process. Just like cooking, you can't bake a cake if you don't know your ingredients. A properly framed project starts by analyzing the physical and chemical properties of the waste stream. It never starts with just buying the technology. Committing to massive infrastructure before you accurately characterize your feedstock is pretty much a guarantee for systemic failure.
Breaking this down, these properties literally dictate your technology. Moisture content is a massive gatekeeper. If your feedstock is basically a wet, organic soup, standard combustion is useless. On the flip side, if it has a high calorific value, it can produce a ton of useful heat, making it perfect for advanced outputs like syngas. We also have to look out for contamination. Things like heavy metals can ruin sensitive catalysts or create toxic ash. And let's not forget supply stability. A multi-million-dollar facility needs a mathematically reliable volume of waste over decades to justify building it in the first place.
Once we know our ingredients, we can pick our ovens. That brings us to Section 4, 3 pathways to power.
This is fantastic because it clearly maps specific ingredients to the right cooking method. It shows that waste to energy isn't just burning trash, it's a highly specific matching process. Thermal pathways use combustion, gasification, or pyrolysis for dry residual waste. Biological pathways leverage microbial activity, like anaerobic digestion, to break down wet food waste and sewage sludge into biomethane. And then you have chemical pathways which use advanced techniques like liquefaction to break down precisely sorted organics and plastics into liquid fuels. The pathway you choose is exclusively dictated by the material you have.
But you know, this science isn't without its tightropes. Let's look at Section 5, Opportunities and Major Risks.
It is a massive balancing act.
The opportunities are incredible, drastically reducing our reliance on landfills, solving severe sanitation issues, and recovering local energy that can actually stabilize municipal grids. But the risks? They are severe. Beyond the obvious dangers of toxic air pollution if emission scrubbers fail, there's a huge systemic economic risk. If you build a plant with massive overcapacity, municipalities get trapped in put-or-pay contracts. That creates this perverse financial incentive to constantly feed the plant with burnable waste, which can literally crowd out and defund local recycling programs.
So, how do we actually navigate those risks? That brings us to our final section, the engineer's decision framework.
Think of this as the ultimate checklist for cautious engineering judgment. Step 1. Always prioritizes reduction and recycling first. Step 2 demands precise characterization of the feedstock. Step 3 clarifies what output you actually need: electricity, biogas, or liquid fuel. Notice how we don't even pick the technology until Step 4, proving that you always start with the waste stream, never the machine. Step 5 verifies all the real-world conditions like financing and environmental safeguards. And Step 6, that ensures we right-size the entire system only for non-recyclable residuals, so we don't accidentally threaten our circular economy goals.
I absolutely love this quote from Vambel and colleagues because it perfectly summarizes the modern environmental engineer's mindset. Older approaches often emphasized landfilling or incineration, while more recent thinking increasingly treats waste as a potential source of new materials, substances, and energy. We have moved so far beyond just wanting to make refuse disappear. Waste isn't a permanent burden to be buried or burned. It is a misplaced resource just waiting for the right scientific pathway to unlock its value.
So I'll leave you with this final, provocative thought. As we expand global infrastructure to meet growing populations, we have to make a choice. When cities build new waste-to-energy plants, are they just reacting to the messy, unmanaged waste we have right now? Or are they right-sizing these complex facilities for a future where we aggressively reduce, reuse, and recycle? Because honestly, the ultimate triumph of waste-to-energy engineering might just be designing itself completely out of existence as we finally perfect the circular economy. Thanks for joining me on this explainer.